So what we've talked about before is we've talked about how to handle definite integrals. So if I have the integral from 3 to 4 of x squared dx, what we talked about prior to this is we said, well, the fundamental theorem of calculus says that in order to evaluate an integral, a definite integral, you take the antiderivative of the inside, so 1/3 x cubed, and you evaluate it from 3 to 4, which means plug in 4, plug in 3, and subtract. So 1/3 4 cubed minus 1/3 of 3 cubed. And then whatever that number is, that's the value of your integral. So the first part of the fundamental theorem says, in order to evaluate a definite integral, you take the antiderivative, plug in the bounds, and subtract. Well, today what we're going to talk about is really part 2 of the fundamental theorem of calculus that says, well, if a definite integral means take the antiderivative, then the derivative of a definite integral means take the derivative of the antiderivative, which just gets you the original. Now it seems like, oh my God, Mrs. Vibert, why are we going to spend a whole day talking about this, or at least, a whole video? Well, it's because lots of things happen. And if you notice, this is kind of an atypical definite integral because instead of two constant bounds, you have a constant and a variable bound. Okay, so this says when you take the derivative of an integral with a variable bound, the derivative and the integral cancel out, and you just get f of x. So what happens here? Well, here's what we have. Every continuous function f is the derivative of some other function. In other words, any function you can make up, I can find an integral such that the derivative of the integral equals your function. It also tells me that every continuous function has an antiderivative, and it reemphasizes the fact that integration and differentiation are inverses of one another. So here's what we're going to do. I'm going to kind of prove to you how this works. So if I want to take the derivative of 3 to the x of 1 plus t squared dt, the integral from 3 to x, here's what I'm going to do. I'm going to forget about this part for a second and say, all right, how would I evaluate the integral of 1 plus t squared from 3 to x? Will I take the antiderivative, which would be t, I don't know why I drew there, that's going to be t plus 1/3 t cubed, and I'm supposed to evaluate that from 3 to x. And that's going to give me x plus 1/3 x cubed minus 3 plus 1/3 3 cubed. Right? So the definite integral from 3 to x of 1 plus t squared is this. Well, I wasn't supposed to just take the integral. I was then supposed to differentiate that integral. So I was supposed to take this and then take the derivative of the result with respect to x. So I'm supposed to take this and then take the derivative of the result with respect to x. So the derivative with respect to x of x is 1, and the derivative with respect to x of 1/3 x cubed, well, bring down the 3, those cancel, is going to be x squared. And then the derivative with respect to x of this, which is technically 3 plus 9, which is 12, what's the derivative with respect to x of 12? Oh yeah, it's 0. So the derivative with respect to x of everything becomes 1 plus x squared. Now let's look at this versus that. Well, wait, they look a lot alike. 1 plus t squared, 1 plus x squared. What really happened here? Well, what happened is that derivatives and integrals are inverses of one another. So when you take the derivative of an integral, what really happens is your derivative and your integral cancel out, and the variable up top here jumps down in for the variable that you see. So let me show you that in a little bit of a quicker way here. If I take the derivative from a to x of sine 3t dt, what's going to happen is the derivative and the integral cancel, and I just really get sine of 3x. The derivative and an integral cancel. The letter up here becomes the letter right there. So the derivative of an integral cancels and you get sine 3x. Same thing over here. The derivative of an integral, when there's an x on the top, the derivative and the integral cancel. The x jumps down in here, and I get the square root of x. Think of it a lot like the square root of x. Come on. technically cancels out. These, what is going on with my computer? These guys cancel. Sorry, it's jumping around. And I just get x. Same idea. Derivatives and integrals are inverses of each other. Now, be careful. Derivatives and integrals cancel out, but only if you have an x on top here. If I want the derivative with respect to x of an integral from a to b, let's think about that. Well, if I plug in an a and I plug in a b, and a and b are both constants, and then I take the derivative with respect to x, you get 0, because the derivative of a constant equals 0. All right, so let's come back down here. Ready? Super, super easy. The derivative with respect to x from a to x, the derivative and the integral cancel. The x jumps in for whatever's here. I don't even need to know what's there. It's going to get replaced by an x. Done. The derivative and an integral cancel. The guy on top jumps in for the letter, ln x squared. I don't even care what the integrand is. The x jumps in anyway. Oh my God, what's happening? I don't care what's happening. The derivative and the integral cancel. The x jumps down in, x times f prime of x. Whatever it is, it gets replaced with x. The derivative in the, wait, the x is on the bottom here. Oh my goodness, that doesn't look like what I'm used to. Well, that's what's great about math. We just take something and say, I don't know what to do with it. So you know what I'm going to do? I'm going to futz with it until it looks like something I used to know what to do with. All right, so I'm really going to take d dx of the integral from a to x. That's what I want it to look like. Wait a minute, wasn't there an integral rule about if I switch the order of the bounds, I negate the integral? Well, yeah, I definitely do that. But I don't really like the way it looks with that negative right there, so I'm going to undo that negative and just throw it out in front. Same thing, right? Sine t dt. So the derivative and the integral cancel. X plops in for t, and then I throw a negative out in front. Done. So long story short, derivatives and integrals cancel out as long as there's an x in the boundary. If the x is on top, it just jumps in for the letter. If the x is on the bottom, you negate it so that it ends up on top, and then they get the negation of sine x or whatever that integrand happened to be. Okay? Now, flip to the back. Derivatives and integrals still cancel, but if this isn't an x and it's an x squared or a sine x or a 1/3 x cubed or an ln x, we have to use the chain rule, okay? So let me show you why. So if I were to say, well, first, I'm going to evaluate this integral. Well, the antiderivative of cosine is sine from negative pi to x squared. And then I'm supposed to take the derivative with respect to x once I'm done. Okay, fine. That's going to mean take the derivative with respect to x of sine x squared minus sine negative pi. Okay, fine. D dx of sine x squared. So the derivative with respect to x of sine x squared is a chain rule. Derivative of the outside, keep the inside, times the derivative of the inside. And the derivative with respect to x of sine negative pi, well, let's see, sine negative pi is 0, and the derivative of 0 is still 0. So here's what I get. All right, so let's look at this. What happened this time? This time, when I had an x squared and a cosine t, it still became cosine x squared, but then I multiplied by the derivative of the x squared. So when you use the fundamental theorem of calculus with the chain rule, you still plug in this top guy in for the variable, but then you multiply by the derivative of the inside. So you plug in the variable limit, or limits, we'll get to that, of integration, and then multiply by the derivative of the bound, the multiplied by the limit of integration, basically. The derivative, pardon me, of the limit of integration. All right, so let's do that for something else. So if I want d dx of the integral from 3 to x cubed of secant squared t dt, same thing's going to happen. This guy's going to plop right down in here, but then I need to multiply by its derivative. So I'm going to have secant squared x cubed times the derivative of x cubed, which is 3x squared. Ta-da! There you go. Derivative integral. Okay, so as long as I have the derivative of an integral with an x on top, the derivative and the integral basically cancel out. I replace the variable with the bound. So t gets replaced with sine x, and then I multiply by the derivative of sine x. Uh-oh, the x is on the bottom. Well, what we saw last time is you can negate it to bring the x on top. So I'm just going to rewrite this as 3 to 2x with a negative out in front. So then when I take the derivative of the integral, they cancel out. I put the 2x in for the t. 1 over 2x squared minus 5 times the derivative of 2x, which is 2, and then bring that negative back right here. So this really becomes negative 2 over 4x squared minus 5. Ta-da! Okay, same thing here. Well, the derivative and the integral are going to cancel as long as I swap this so that the x is on top. All right, fine. Plug this in for t, negative 3 over 5 minus 25x to the fourth, because I squared 5x squared, times the derivative of 5x squared, which is 10x, and then bring this negative back so that becomes a positive. So I get 30x over 5 minus 25x to the fourth, and you can leave it like that. We don't need to simplify. Okay, what happens when there's two bounds? Well, basically, the backstory of what I'm about to do is you can separate this, and I can rewrite this as d dx of the integral from x squared to 0. I don't even care. It doesn't even have to be 0. Here, we'll call it a. X squared to a. Sure. T plus t squared plus the integral from a to x of the square root of t, t plus t squared. So really what we can do is just say, well, there was that rule that if the top bound and the bottom bound match, you can combine these into one integral. But really what ends up happening is the derivative of this integral ends up being negative. The derivative of that integral ends up being positive. So really, long story short, you just plug in both bounds and subtract them. So when I plug in x, the derivative of the integral cancel out. And when I plug in x, I get the square root of x plus x squared. And then when I plug in x squared, I have to negate it because it was on the bottom. And I have the square root of x squared plus x squared squared, which is x to the fourth. Then times the derivative of x squared, 2x. So when you have bounds where both are letters, what really happens is you plug them both in, you multiply by both of their derivatives, and you subtract. So same thing right here, and we're done. When I take the derivative from sine x to x squared of ln t dt, the derivative and the integral cancel, and I have ln x squared times 2x minus ln sine x times cosine x. I plugged in the bound, I multiplied by its derivative. I plugged in the bound, I multiplied by its derivative, and la-ti-da, I'm done. All done. Long story short, derivatives and integrals are inverses of each other. So when you take the derivative of an integral, if x is in the boundary, you just plop in the x. If it's something other than x, you plop it in and multiply by its derivative. And if there's no x in the boundary, like this one, you get 0. I am done. There's the Fundamental Theorem of Calculus Part 2, and that's it. Have a good day.